Okay.
Oh, very good.
It's my big pleasure to introduce Sean Keel from University of Texas in Austin, and Sean will talk about mirror symmetry in analytic disks.
Thanks. It's cool to be here. I think this is I think. Oh, can you get? Oh, just a second. I want to get rid of this thing here. There, it's gone. I think this ZAG thing is cool. I mean, I've watched a lot of talks on it. I really appreciate it. I'm talking about work with Tony, who's here. Tony, are you actually here? I just see a frozen image of you.
Yes, I am.
Yeah. Oh, very good. Anybody who is willing, it really helps me out if I see you on the screen, just because then I can see just how poorly I'm doing. But you do what you got to do. I appreciate those of you who are here. I appreciate it a lot. Okay, so here's the setup. I'll get to something fun in a minute, but let's start with just a super basic thing. So basic to what we're doing. So K is going to be a valued field. What does that mean? Well, it means it just means we've got a function. We'll write it as little norm. It's a function from K to R greater than or equal to 0. And what properties does it have? Well, it's like a norm. X, Y is norm X, norm Y. I think we need the condition that the norm of 0 is 0 and the norm of 1 is 1. And then it satisfies it's what's called a non-Archimedean norm. It satisfies the strong triangle inequality. So the norm of X plus Y is less than the max, norm X and norm Y. Equivalently, we could have written it, why am I calling it valued field? In terms of the so-called value, the valuation, that's just minus the log of the norm. And then, so that would be a map from K minus 0, that'll go to infinity 0, goes to R. Okay, so what are some examples of this? Well, so what's an example? Let's say R is a discrete valuation ring. You probably know what that is. And then you can just take K to be the quotient field of R. So it comes with a valuation. Another example, though, so we could have, say, QP, or we could have power series. But another example is amazingly useful. This will actually be the main thing that we do, is we can just take K to be any field at all and just take the trivial valuation. So that just means, what does that mean? Just, I mean, totally trivial. The norm of everything is 1, less X is 0. That this could lead to an interesting theory is maybe a bit surprising. And now here is a key definition that just a really innocuous looking definition that hides a ton of rich stuff. I wish I'd come up with this definition. I did not. It's due to Berkovich. So let's say I start with X. Sorry, X is going to be a scheme over such a field, K. And then the analytification, it's a set of pairs, X and W, where, so K has this valuation, I'll call it V. Where X is just a scheme point of little x is a scheme point of X, and then W is a norm on, or valuation on, the residue field that extends the given one. That extends, which is on K, of course, sits inside of the residue field K of X. So you just extend the valuation at each of the points of the that's what this is. Always to extend the valuation. So this is the key object. So what can we do with this thing? Well, of course, notice let's talk about it a little bit. Let me, the Berkovich analytification comes with a map to X. Just forget the value W, and forget the valuation. And then also, if I take a regular function on X, then I get a map of this thing to the reals, which just takes the pair X and the norm to, well, just to evaluate the norm, just take the norm of f of X. So that gives you a map, and we want and then we make this into a topological space by insisting that we make these continuous. And now it's actually, it is a very nice topological space, which I'll stress here in a second. It's a very nice topological space. Nothing like the Zariski topology. This is a much more serious topology. But let me also mention that this X is actually way more than a topological space. It has a natural ring of analytic functions. So it's a ring space. It's a ring space. And I hardly ever, I use these analytic functions. I almost always only use algebraic functions. But I think Tony and I finally are going to need some analytic functions. But in any case, just I mentioned that, so you don't need to be too worried about them. I am not worried about them. The thing from X goes to X analytic, that's a functor. From schemes to these things, there are more general things, which I'll mention some, which are called, these are what's called a K analytic space. K analytic space. And this functor, the reason you already know a ton of analytic geometry is there's a Gaga principle. So this, if we stick to projective schemes, then this is a fully faithful functor. So you don't gain any information, just like the ordinary analytification, complex analytification of a variety over C. Okay, so let's say, let me say, what else can I say about this thing? Well, let's say that, notice that the K points of X just sit naturally inside the analytification. Because these are, what are these? These are the points X such that the residue field of X is K. Well, then you have no choice. Then W, then the valuation you put there has to be equal to the given valuation on K. So these just live inside of here. And I think of that as saying that algebraic geometry, is inside this object. But the really cool thing is, as we'll see over and over here, is that it's got algebraic geometry in it. It's also got tropical geometry inside of it. So, there's also tropical geometry. We'll see that over and over here. Geometry is, and let me illustrate how that goes. So what's the, let me just mention now about the topology. So I told you it has a nice topology. This topology is locally compact, path connected. Let's say that's if, or locally path connected. Let's say X is integral. Then it's path connected Hausdorff space. Hausdorff. Why do I mention that? Because this thing, because of the weird triangle inequality, this XK, there's a totally disconnected set. Totally disconnected. This other guy is just path connected Hausdorff space, and this, except when K is trivial, this is dense. So you start with this totally discrete thing, and it fills it in canonically. It's like you start with algebraic geometry. It's got this totally discrete thing that people used to study when they studied, like, p-adic manifolds. Totally nasty object with no reasonable theory of analytic continuation or anything, and it just canonically fills it into this path connected space. Let me give you a quick example, maybe the only example that I have some feeling about what the thing actually looks like. Let's take X to be P1, then this analytification, it's a tree. It's what's called an R tree. So it's a tree, except the R thing means that there can be infinite valence. At some of the points can have infinite valence. But let me draw a little picture of how you can see it. So here we have this. Here we have X analytic. We said this is a tree. The rational points, again, Kx here is P1. The rational points, so that's just K union infinity. That sits inside of here. These are leaves of this tree. And let's take, it's hard to draw this tree because of the infinite valence, but let's say we take finitely many of these points. Let's say we take P1 up to Pn in Xk. So those are some points, some leaves of the tree. And then it's a tree, so we can take their convex hull. We can just take the smallest subtree that contains these points, just in the most naive way. And this is a really beautiful thing. What you get is this object, this convex hull. Let's call that thing the skeleton of X0. X0 is just X, throw away the points. The skeleton of this, that's this. This is an element of M0n trop. Meaning it's a metrized tree, metrized graph, metrized tree with, these are the points here, as labeled vertices. So it comes with this nice distance on the thing. So this is living. So now we see that, we take this X0, that's just P1 minus some points. Inside of it, so we said, what do we have in here? We have, we had algebraic geometry already in there. We had the K points, but here we have the skeleton of it. X0, living in it. This is the tropicalization. So this is a tropical curve. This is the tropicalization of X0. But in this world, it lives inside the space, the manifold. I mean, this is like a manifold. It's smooth. It has holomorphic functions on it. but it has this tropical curve living inside of it. Moreover, we have a canonical retraction from X back onto, let's say X0, but we could also say X. Let's just say it goes all the way to X, to the skeleton. So onto this tree, there's a canonical retraction. That's true if you have any subtree of any tree. You have this retraction. This is actually deformation retraction. It's due to Berkovich. Let's just do a simple example of that. Yes, and then I can draw a little bit more picture of what X looks like. Let's just take case of, say, 2 points, 0, infinity inside of xk, and so then our x0 is just gm, complement of 2 points, and here's the skeleton. This is the skeleton. It's just 0, infinity. It's really the closure of the skeleton. And then we had the X analytic has this retract onto here. Well, it's a big tree, so maybe I'll draw some junk here. It goes off, in all directions. All this tree retracting down. Can't draw it all over the place. But let me just say that. So each point here will have all kinds of stuff. A gigantic tree retracting back down onto it. Switch to the next page here and say a little more about this map. Look at this X analytic going down. Inside of here, we had the K points again. That's just, again, K union infinity. And this map, this is just 0, infinity. This retraction map on the K points, this is just the norm. So this is just take norm. Take the points, take the K points, take the norm. So the fibers of this retraction, what are they? Well, they're tori. I mean, they're the set of X such that the norm of X is some constant. So, so this is a torus fibration. This is a torus fibration. This is the first example of the Berkovich version of the SYZ fibration for mirror symmetry. It just comes for free. These things just come with these torus fibrations. There's some singular fibers. In this case, there's only 2. Just over 0 and over infinity, there's only 1 point. In this case, over the whole GM, all the fibers are tori. This is an honest torus fibration. This is where I think Savage and Soibelman were the first people to say, there was this SYZ conjecture in mirror symmetry that said Calabi-Yaus should fiber in compact tori over a real thing of the same dimension, so the same real dimension. And that conjecture has not been proven. There's some examples of it, but they observed that, look, in Berkovich geometry, we have this thing right from the beginning. So maybe that's the right place to go. So we have this SYZ fibration. Notice, let's still draw this picture here, and let's take like some little d, and let's take the inverse image of 0d. I'm going to call that thing d0 because here's 0 and here's infinity. And conceptually, so what's the picture? So the inverse image X. This conceptual picture, the inverse image, of course, it's the inverse image of the whole thing, is broken up into the inverse image of the first interval and the second interval. The point is, why am I saying that? This is a K analytic disk. This is a K analytic disk. I mean, its rational points are just norm X less than or equal to D. So this is an honest to God disk, just norm less than D. This is a disk. The P1 breaks up into a disk around 0 and a disk around infinity. And one of the things that really attracted me to the subject is that this object, D0, this is a perfectly nice K analytic space. Perfectly nice K analytic curve. It's like an algebraic thing in this world, this curve with boundary. And it in this world is perfectly reasonable to have P1, broken up written as a union, decomposed as a union of 2 disks. That's a pretty nice thing in mirror symmetry, which we'll get to, which is all about disks. So the disk is just a natural object in the Berkovich world. Let's see, anything more about this example? I don't think so. Let me just extend this. That's another example. Well, so let's suppose I take some U. Again, these are varieties now over K. Sitting inside of Y, let's make this an SNC compactification. And now I'm going to say that K is trivially valued. This is not at all important for what I'm saying. But then what I would do instead was, for people to know the world a little bit, otherwise I'd have this U, it would be defined over say power series. I would take a model of it, take it over over a formal disk, and then I would want that family to be semi-stable. That would be my version of an SNC compactification. And almost the same thing would be true. But let's just take an SNC compactification, ordinary old SNC compactification, and let's take sigma to be the dual fan to the boundary, to D. D means the boundary of U, meaning y minus U. So let's say this is, sorry, y minus U. Yeah, so this is, D is D1 plus Dn. So what's the dual fan? This is just a purely combinatorial abstract. So what is the dual fan? This is just an abstract fan. By abstract, I mean it doesn't come living in a vector space. It's just a simple thing. So it has rays corresponding to the irreducible components. D1 up to Dn. And then I have a bunch of rays. Let's say I have Di1, Dik. These rays form a cone, or span a cone, let's say, span a cone. It'll be a simplicial cone, span a cone, if and only if Di1 intersect Dik is not empty. So let's, for example, we take simple example, let's take Y to be P2, take the standard toric boundary, D to be just XYZ equals 0, the standard boundary, and U is the complement, Y minus D, which is GM squared. So in this case, okay, what's the dual fan sigma? Well, it'll just be the toric fan. If you know toric geometry, a little toric geometry, so it'll be the toric fan. But anyway, what is it? So it's an abstract fan. It's got one ray for each of these three divisors, sort of D1, D2, D3, corresponding to D1, D2, D3. These are just abstract rays. And then, okay, what about there? Do we have a cone here? Yeah, because D1 and D2 intersect. So this point corresponds to this cone, etc. D2, D3 corresponds to this, etc. We have this thing. Okay, so we have this abstract dual thing. And now, so what? Well, the point is that the underlying topological space of this fan, it lives inside of U analytic. So this is again a version. This is like a minute ago when I had P1 and I had this graph living inside of it. This is a kind of tropical thing, or convex geometry type thing. Think of it as roughly Rn. It's like an Rn. At the moment, it's just it's abstract fan. It can have all kinds of topology living inside of here. And how does this work? How? Well, so let's how is this working? Here's this fan. Well, let's first take so this is a picture of the fan. This is the dual to XYZ equals 0. So P2. Each of the divisors, if I take DI, so note, if I have any U birational to some Z, so take some variety birational to U and take some effective divisor on Z. Okay, so this is like and we take some divisor on it. Well, what does E give us? E gives us a valuation, let's say val E on the field of fractions of U, on the function field of U, just namely val E of F is the order of 0 or pole, along E. And so we get a point of, we get a point of E inside of the analytification. Namely, I have to give you an X and a valuation. For X, I take the generic point. So that's the generic point of U. And for W, I take this valuation given by E. Okay. So every divisor gives me a point in this way inside the analytification. And also, this is one of the things, because K is trivially valued. Well, okay, maybe that was, I should have said that second, but I can always just multiply. I can scale a valuation by some positive real number. You can just scale it, and because the K is trivially valued, that scaled thing is still inside the analytification. Still restricts to the trivial valuation. So, okay, back to my picture here. This was the class of, say, of D1, but then I also have twice D1, and 3 times D1, and so on, going along there. And here's maybe D2 and all the multiples of D2. D3 and twice D3. But then what are all these other points? There's loads of other points here. Other kind of abstract integer points, loads of ones like here. Sort of, kind of D1 plus D3. That doesn't make sense. You can't add valuations, but inside this cone, I can add them. This is just a simplicial cone. This is like n squared. So I can just add, that's what I mean by this point. What does that correspond to? Well, all these other integer points, these all correspond to all the other points. You can't read that, but all the other points of these integer points here. Sorry, that's the wrong notation. That's what I mean. Integer points. These correspond to divisors on blowups. These are divisors on blowups of y. So, for example, what was our picture again? This was YD. This was our YD. Here was D1. Here was D3. Here we have this point here. We can blow it up. We'll get a picture that looks like this. And then we'll have a new E. And then we have the class of E inside the skeleton, inside the analytification of U. And what is it? That was that point. So here, back to the dual fan. Here was D1. Here was D3. That was that point 1, 1. Kind of, this was sort of D1 plus D3. Okay, so maybe this is familiar to you if you've done any toric geometry. These integer points correspond to the valuations given by blowups on blowups. And then it's a little bit more subtle, but not all that hard. There's a real interpolation to fill the whole thing in. Because, it's the whole, all these real points, the whole damn thing lives inside of the analytification of U. You can write down valuations correspond to these, in terms of local analytic coordinates of power series. You can write down, they're so-called monomial points. So let me make a remark. So if ky plus d is nef, so for example, if it's trivial, this, by the way, says that U is log Calabi-Yau, then this underlying set of sigma living inside the analytification of U, we call it the skeleton of U. It is canonical. It does, it depends only on U, not on the compactification. It depends only on U, not on the compactification U inside of Y. And then different Y, just break it, give different Y, give it different fan structures. Different Y give it, let's say, divide it into cones in different ways. Just like in toric geometry. In fact, that's just an example of this. For example, if U is Tm, so M here is isomorphic to z to the n, it's a lattice. And then Tm, that's my notation for M tensored with Gm. So this is just the algebraic torus with one parameter, with co-character lattice, with co-characters, character lattice equals M. So in this case, the skeleton of U, the integer points, are canonically M. And then the skeleton is just MR living inside of U analytic. So this is this generalization of this. And just like before, we always have a retraction of U analytic onto this guy. And let's stick to the Calabi-Yau case now. So we have this retraction. And so this is the Berkovich retraction. We'll call this the SYZ fibration. Let's say we're now in the log Calabi-Yau case. Let me just remark that in general, the dual complex, so the dual complex, in general, what I mean is just take any, take any SNC pair YD, form this abstract cone that has no properties. I think Kolar proved that that this can have absolutely, you can get absolutely any topological space here, or maybe any simplicial complex. It has sort of no, they have no properties at all. But remarkably, in the Calabi-Yau case, it's very restrictive. Log Calabi-Yau, also Calabi-Yau, very restrictive. For example, Kolar with, and maybe it has to do with Zhu and de Fernex also. They have a bunch of papers about this topology. It's a, the skeleton of U is a Q homology Rn. Homology Rn. I believe it's an open question whether it isn't always just Rn up to quotient singularities, like an orbifold version of Rn. Maybe that's only a conjecture or a question for compact Calabi-Yaus, but I personally don't know an example where the topology is much different than Rn. Oh, and let me say more about this retraction. That's also true in the Calabi-Yau case. By the way, let me just use a notation here. Notice that the dimension of the skeleton of U, just by construction, is less than or equal to the dimension of U, and it's called maximal boundary. That means equality. So that's the case we're always going to assume we're in. We're always going to be in that case. And let's talk more about this SYZ fibration, the retraction to the skeleton of U. And this, remember, this has this fan structure on it. Has this fan structure, and what's true is that in the log Calabi-Yau case, outside codimension 2 in the target, this is a torus vibration. This is again a torus vibration. It's isomorphic to, so let's say, what I'm saying is, let's take a outside of some codimension 2 set. So in this two-dimensional case, it would just be outside of 0. We take a little convex subset of this, this is just R2. We take a little convex set G inside of one of the maximal cones of the fan, and let's take script G to be R inverse G. It goes by R down to G. This is just isomorphic to the toric case, the Taurus case. What do I mean by that? I mean, do the same thing where U is TM. Then, then this picture is just the fan, the fan of a toric variety. This is just a box in a lattice, and this map from TM analytic, that's GM to the N, as a map by R to the skeleton of TM, which is just MR. This is just the map that we had before. This is just the norm. This is just the norm on the coordinates. So this is just an honest torus vibration. Honest torus vibration. Torus vibration. And the theorem is it's isomorphic to and the theorem here, which is easy. I don't mean to belittle my coworkers' result. This is a result of Tony, of you, Zhu, and Nikes. I won't try to spell his name. They prove this thing that in the Calabi-Yau case. So in the log next page, log Calabi-Yau case, where I go from U analytic down to skeleton of U, that outside codimension 2 in the image, it's isomorphic to the torus case. Okay, so what, this is going to be very important for us. This means, in particular, that inside of U analytic, we have lots of, let's call them torus pieces. This script G that I talked about, R inverse of G, this lives inside of U. It's what's called an analytic domain. Analytic domain. This is actually an aphanoid analytic domain. And it's a standard piece. This also lives in a torus. TM analytic. And there's a topology, the so-called, in the G topology, there's a Grothendieck topology on these things. This is an open set in that topology. In this, not in the Berkovich topology that we talked about, but in another topology that's in this world, basically perfectly nice object inside. We have this nice open subset, which looks like a piece of an analytic torus, and we have this retraction. Okay, and we'll get to that in a second, why this is interesting. Okay, so this was a little introduction to Berkovich geometry, and now let's switch gears just slightly and go to mirror symmetry. What's the connection to mirror symmetry? Oh, sorry, I should have let me just mention one more thing before I do, because it'll motivate it. Notice we said that we have the skeleton of U. It's got these integer points. And when U is a torus, this is just M. That's the co-characters. And now notice, this is a basis of functions on the dual torus, which is just Ham M to GM. I mean, these are just the characters. These are these are the characters of the dual torus. Characters of the dual torus. They're monomials. They're the monomials in it's just, the functions on the dual torus are just ZM, just Laurent polynomials with exponent M. In M, these are just the monomials. So this is a basis of functions. The skeleton is, in the torus case, is a canonical basis of functions, not quite on the variety, but rather on the dual variety. And our conjecture is, is that this is true. This will be true for all log Calabi-Yaus. It's a maximal boundary. And in particular, we can just say we can build, so we can make the homological mirror symmetry mirror to U, which now is going to be an affine log Calabi-Yau with max boundary. And I'm just going to build for you the mirror. How am I going to do it? I'm going to define the mirror as just the spectrum of some algebra. And what's the algebra going to be? Well, I'm going to start out, it's not going to be quite right, but this is more natural to start it with. I'm just going to take the free abelian group with basis the tropical set, the skeleton, the analog of the co-characters in the torus case. So just as a matter of definition, that means it's a direct sum of Q in the skeleton here of Z times theta Q. That's just formalism. It's a free abelian group. This is what I'm with a given basis. I'm just calling theta Q the basis element. This is nothing, just pure formalism. So the conjecture is that this is a ring. So the conjecture is that this thing, that A has a natural ring structure, and then much more than that, that the spectrum of it is the homological mirror symmetry mirror to my original variety. So if I want to build the mirror, I just have to put a ring structure on this free abelian group. So I have this free abelian group, Z times theta Q in the skeleton of U. And these are these boundary divisors. These are all these divisors. And we want a multiplication rule. We want this to be a ring. Well, what does it mean to make a free abelian group into a ring? You just have to say how to multiply the basis elements, right? So that means I need to know what theta P1, theta Pn is. And whatever it is, it lives in this free abelian group. So it has a unique expression as some coefficients, P1 up to Pn Q, theta Q. You know, just expand out the product in the basis. These are what are called the so-called structure constants. Structure constants. So I just need, and there should be some integers. So we need some integers. So you give me P1 up to Pn and Q, and I need an integer. And in fact, we're going to give a positive integer. We're going to give an element of z greater than or equal to 0, and it's going to count something. Count something very natural. Something natural. Okay, so you know, maybe we got plenty of time. Maybe let me just, you know, in case I've lost you a long time ago. Let me just say where we're at here. We're starting with U. It's a Calabi-Yau manifold. U is this log Calabi-Yau. What does it mean? It's affine. Log Calabi-Yau means it comes with a volume form. So U has a canonical volume form. Omega, a top degree, you know, algebraic differential form, volume form. And by the way, we can say just I can just repeat again, what is the skeleton in language just having to do with this? What are the integer points of the skeleton? This is just the set of all divisorial valuations, discrete valuations on the field of rational functions. What's a divisorial discrete valuation? It's the valuation given by a divisor on some variety with that field of functions. So the valuation, these are the, this is something like some val E that I talked about before. It's these guys with what property, let's say valuations V, such that V of omega is negative. Union 1 extra 1, the 0 point, the trivial valuation on the generic point. That's what the skeleton is. So these are roughly, you know, so an element of this, you know, is a pair of a divisor E, that's a divisor on some compactification, and then M is just an integer, it's a multiplicity, integer, and omega has a pole along E. That's the set we're talking about. So start with a Calabi-Yau, take this set. I take the free abelian group with this basis, and I'm telling you it's a ring, and I'm going to tell you what the ring structure is. Okay, so let's get to the ring structure. So again, what are we given? So we're given P1 up to Pn and Q, and we think of them in two different ways. So we start here with U inside of Y. This is a SNC. Let's say KY plus D is trivial. Let's think of this P1 up to Pn. I'm going to think of these guys as boundary divisors, like the case of when I had 3 lines in P2. So this is so P1, I'm really going to think of that P1 is M1 D1. It's a multiple of a boundary divisor. M3 D3. It might not have, these divisors might not have lived on Y, but they just live on some blow up of Y. So for simplicity, let's just put them on Y for the picture. So that's what I'm thinking of as I give you 3 boundary divisors, each with a multiplicity, an integer multiplicity. But then Q, I think of in a completely different way. Q lives in the skeleton of U. And that lives, this is, you know, a Berkovich thing, that lives inside the analytification of U. So there's Q right there. And what am I going to do? I'm going to count maps. So what do I count? I want an integer. I'm going to a structure constant. I'm looking for a number attached to this data, positive integer. I'm going to count something. What I do is I count disks, maps of a disk. I'm going to have a disk. So I fix a disk, an analytic disk, a disk D with points, P1 up to Pn and one more point, little q. So here's some points. Here's Q. And I count maps. Let's call this disk B. I'm going to count maps F of B into Y, and I'll draw conceptually what they're going to look like. they're going to touch the boundary only at the given points with the given multiplicity. That's the disk. And then it's also going to pass through Q. That's the things I'm going to count. So I'm counting disks. They only touch the boundary. They live almost all in U except for the marked points. The marked points touch the prescribed boundary divisors with the prescribed multiplicity. And the last point goes to this fixed point Q. So yeah, so precisely what was the thing? So F inverse of D is the sum MIPI, and F of Q is Q. So here I'm counting analytic disks. Now this is an infinite dimensional space. If you count disks, you can't control them. They're infinite dimensional. So we need a boundary condition. And we're going to ask that the disk extend to a map. So here's the disk. I'm going to ask for a P1 to be decomposed into two disks, my disk B, and then I'll have one other disk, I'll call it D, let's say D infinity. It's going to have one extra point on it. Here's all the original points. That's going to be my curve C. And the subtle thing is, now C is going to map, but it's not going to map into Y. So what did I do? I had a disk mapping, I had the disk going into Y, going into Y, the analytification of Y. I need some place to stick these end disks. And what I do is I just glue on an artificial end to the disk, and that's where this end disk is, sorry, an artificial end to Y. I'm going to glue on a toric variety, basically a torus, actually a toric variety. We glue on a toric variety and we send this second disk into that toric variety. Let me just be precise. So what was our picture here? This is the picture of the skeleton of U, which is the support of this fan. And we had this point here, Q. And I told you that locally, and we have this retraction map, this SYZ fibration from U analytic to the skeleton of U. This is the support of this fan. And this is locally just the map of a torus to MR. So we have the same little box. Take a little box here. We have the same little box sitting inside of here. This was my G. And I have this little box inside of here, G. I mean, literally a box. This is just, simplicial cone. I just have a square inside the cone. Here, these are always the retractions. And this is, our inverse of the box. That's this G. So as I said, we have this box script, or this piece of a torus living inside of our U analytic. So I can just glue on TM, the torus along here. So that's what I do. So I'm going to take V to be U analytic. I glue along this common toric piece with the torus. And now I want a slight compactification. That's going to be Y analytic, U along T, with a toric variety, but a very simple toric variety. It's just the toric variety with a single boundary divisor corresponding to, any normal person would think it was going to be Q in M, but it actually is minus Q in M. Corresponds to minus Q. So if you know the toric geometry, I mean, in other words, the fan has just a single ray, R greater than or equal to 0 minus Q. But anyway, this toric variety is just a torus. It's, GM to the N union a single boundary divisor. Let's call it D sub Q. It's really D minus Q. That's just a GM, one smaller GM. So it's just P1 cross a torus. A1 cross a torus. It's just A1 cross GM N minus 1. Okay, so that's this thing we're going to call this we're going to call Z. Sorry, not Y. We're calling that Z. So okay, so what do I do? So I had my disks. I had my original disk mapping into Y, but I ask that this extend, this map F extend. This sits inside of Z. This sits inside of, that was the original disk. We have this new disk. It has one more marked point, Z, going into, this is where our original points were. We ask of a map like this with this, with the same conditions. What do we ask? that f of b goes inside of y, f of this dz, the extra disk, that goes into the toric variety. And the same condition as before, the boundary of z, what should it be? It should be those points, mi, pi, plus it's the multiplicity of q at z. So we have one more point of contact at this little point here. Okay, so what do? We just counted disks in a pretty naive way. Then we had one smart idea, which was to ask that this map extend to this disk. I'll tell you, this smart idea is due to Tony from before I met him. Almost very early on when I was talking to him, maybe this 10 years ago, he already had this idea that you could take a disk and you could complete it, and you could glue some junk onto the Berkovich space. That made sense. That this Z, by the way, this is a perfectly nice. This is still a smooth K analytic space. It's not separated, but so what? It works fine for deformation theory. Okay. And now what's the final statement is? So what's the statement? Let's get to the thing. So now the theorem is that for general choice of the points. Oh, sorry, one more thing. I'm counting rational curves before I get to the theorem. I'm counting rational curves. I can't count rational curves until I fix their class. I haven't fixed the class yet. So to count, stable maps, P1 analytic into this Z, I need to fix a class. And a cool thing in this world is the disk itself into Y, this B going into Y, this has a well-defined class. Even though this is not this curve has a boundary, there's still a well-defined cycle associated to it. And that just lives in the Mori cone. It's an effective curve class, lives in the Mori cone. So now the choice is, so for general choice of points, and a fixed beta, this moduli space, the moduli space of such disks is a set, is a finite set. Is smooth, zero-dimensional. So we can just take its cardinality. So we can just count it. We can take just the number. We don't need any kind of virtual fundamental class here at all. We just naively count disks mapping into our original U analytic that admit this compactification with a little standard end on it. And then what's the theorem? Theorem, this is Keel U 21, is that this works. So now, so I should say, because I said I added the data, to get a number, we added the data of beta in NEYZ. So now you give me P1 up to Pn, Q, and beta, and I give you a number. Q beta, that's this count of disks. So now the right algebra to take is not a free abelian group, it's a free module over Q, still Q in the skeleton of Ry theta Q. What's Ry? Ry is the monoid ring of the Mori cone. That might sound pretty fancy. That just means the direct sum over all beta curve classes in the Mori cone of integers times some z to the beta, just multiplying in the dumbest way. Z beta 1 times z beta 2 is z beta 1 plus beta 2. So we have this free module A, which again just direct sum of these theta Q here, Q in the skeleton. And the theorem is that these counts make a finitely generated commutative associative Ry algebra. Of course, it's obviously flat. It's even free. So I get a family from it. If I take X to be the spectrum of A, I get a map to the spectrum of Ry. That's a natural object, by the way. That's the toric variety given by the Neff cone of Y. Inside of here, we have the torus given by the Picard group of Y. And let's just take the restriction of this map. Let's call this P. Let's call this P. Let's call the restriction V. And what are the properties of this map? I said that it works. What do I mean by it works? So the theorem is that the fibers of P are, well, they're Calabi-Yau in some sense. So they are Gorenstein. That means K makes sense. K trivial. That means they're Calabi-Yau. SLC, semi-log canonical. That means they're reasonably nice. Affine. And over T pick Y, if we restrict to the structure torus of the target, the torus in the target, then the fibers are also canonical. Fibers are normal. So that means that they're log canonical. So these really deserve, these are log canonical varieties with affine varieties with trivial canonical class. I mean, these are Calabi-Yaus, of course, and they're the same dimension as U. And now we conjecture that A is the symplectic cohomology of U, the zeroth piece of the symplectic cohomology, and that this is this family X, or maybe V, this is the homological mirror symmetry mirror. We don't know that this is true, although I think now it is known in some cases that this is true. Who cares if you don't care about mirror symmetry? So who cares? Why should you care about this? Well, let's say one thing that's kind of cool about this. Whatever they are, note that the fibers V of this family that we just built over the torus. Notice this is just GM to the size of the Picard number of Y. The fibers, these are affine varieties, and they come with a basis of functions, which I hope seems strange to you. So this is an affine variety with a basis of functions. Basis, canonical basis of functions, and moreover, its whole ring, the ring structure on this affine variety, on the functions on this affine variety, is given by counts of disks on U. So it's a pretty cool thing. And now mirror symmetry is supposed to be an involution. So mirror symmetry should be involution. So if we do it twice, we get our original U back. So even if we don't care about mirror symmetry at all, we have this affine Calabi-Yau, of which there are many interesting examples. For example, all the open Brujas, double Brujas cells in a semi-simple group is an example of these things. Or lots of different character variety of a punctured torus, of a punctured Riemann surface is an example. So there are many very interesting varieties. We get our original U back, but now with a canonical basis of functions, which we didn't have when we started. Basis of functions. So in particular, we have the conjecture that an affine log Calabi-Yau with max boundary should have a basis, have a canonical basis of functions. And this has actually been proved now in dimension 2. This is true in dimension 2. It was very recently proved by my former students, Jonathan Lay and Yan Zhao, building on work of myself, Gross Hacking Keel, from I don't remember when. So we had a preprint that did some version of this, and then they made it nice. So they proved it. What they did was they took this family that we build, and they proved that it was the universal family of Calabi-Yau, of log Calabi-Yaus in dimension 2. So they just proved that the family we get, those are all the Calabi-Yaus. Look, they have a canonical basis of functions. That was their theorem. Okay, so basically that's it. That's what I got to say. Thanks.
Thank you, Sean. Thank you very much. Let's thank speaker. And then Zoom. One moment. I stop the recording.